Okay, then let's continue. So, yeah, so the next thing to talk about is how to find such estimates. So, like I said, the maximum likelihood estimator is defined as the value in parameter space that maximizes the likelihood function over all possible values of the parameter. And the common approach to actually do that using then, going down the analytical way and also featuring prominently in the numerical maximum likelihood estimation procedure is to compute the derivative of the likelihood function with respect to the parameter. So something that one can write like this if you go also over my basic calculus. And so one needs to compute the derivative of the likelihood function with respect to the parameter. So very in analogy to what we've seen for the calculus refresher, where the x, so remember there was the x, that was a function of x, that would be, x would be the parameter theta. Yeah? So you compute the derivative of the likelihood function, and then a necessary condition for the case of a maximum is that at the location of the maximum this derivative is 0. Yeah, so this is an analogy to what we've seen before, that we do this f prime x set to 0. Yeah. This notation is a little bit more general and also accounts for the fact that, or not quite, but can be extended to the case that theta is actually multivariate. So this, of course, here the x was a real number, and we've seen already for the GLM that our theta is actually p dimensional times this for the GLM. So this is more like a general idea than now actually telling you how to compute this in a very specific context, because then you would have to evaluate the gradient, and we haven't discussed what the gradient is. But that's fine. The general idea is that you compute the derivative of the likelihood function with respect to the parameter and set this to 0, and then hope that you can solve this analytically for some value of the parameter. And that's kind of going down the analytical route. To help that, and also to see this more concretely in an example in a second, what one actually usually uses instead of the likelihood function is the so-called log likelihood function, which which would be the next thing. So now the topic is log likelihood function. And the log likelihood function is defined as follows. So I use a small l for it. The likelihood function has a big L. It again takes parameter values in and returns real numbers, not only positive numbers, but also negative numbers. And it takes parameters in, maps them onto values, and it's of course dependent on the data as was the likelihood function, and is defined as the natural logarithm of the likelihood function, yeah? Which is of course the same as the natural logarithm of the definition of the likelihood function, which is the probability of the data for fixed value for the values of theta, or in more specific cases, of course, the probability density. Now, why is that done, and why is everybody always talking about the log likelihood function rather than the likelihood function? So there are So the main reason why this is done is just because of pragmatics. Often there are pragmatic reasons to use the log likelihood function instead of the likelihood function. One is that these kind of probabilistic models often contain exponential terms. We've seen that for the Gaussian, and then I hope you looked a little bit into it, that the logarithm of the exponential is the identity function. So the good thing is that if you take logarithms of exponential things simplify. So it's mathematically simpler. That's one good reason to use the log likelihood function rather than likelihood function. And another reason that helps is that if you think about the log, then the logarithmic function looks like this, and often for probability densities and probability values, you are actually here. So your p theta y would be somewhere between 0 and 1. So that stretches this interval over a very long range here. So you get a little more sensitive, and also in terms of the numerics of things. But this also shows that the log likelihood can also be negative. Yeah? So don't get confused if you see negative values for the log likelihood and then thinking about, but why the likelihood is supposed to be the probability, density probability of data for a specific parameter. The log transform can make it negative. Yeah, the last thing that I was always worried about is, okay, when I find a maximizer of the likelihood function, then I have a maximum likelihood estimate. But now if I maximize the log likelihood function, is this actually, does this imply the same value in terms of the estimate or estimator? And the answer is yes. The thing, and it works because the log function, so the natural logarithm, is monotonically increasing. So essentially, when you have a higher value in the likelihood function, you also have a higher value in the log likelihood function. So the value in parameter space that you find by maximizing either the likelihood function or the log likelihood function is the same. Yeah. So there is, one could basically show that more formally, but yeah, it's also it works because as you can see, the log likelihood, the log function does not go down at a specific point, so that then if you transform things to log space, that then suddenly your estimates, your maximum likelihood estimates would lie somewhere else. It also preserves, because it's itself a concave function, it also preserves the fact that if the likelihood function is concave in the first place, then the log transform of it is also concave. So in terms of using the idea of, or capitalizing on the fact that a function has a well-defined maximum, the log also doesn't interfere. Yeah. So in the script, I then also explain a little bit about concave functions. I will not do that now. The thing is, for concave functions, it's guaranteed that especially for strictly concave functions, it's guaranteed that there is a maximum that you can actually find. For all other functions, that's not the case. So if you ever look into numerical mathematics, there is a big field called convex optimization. Convex is the inverse of concave, and not the inverse in terms of mathematics, but in terms of concept. That's why that's the reason why numerical mathematics is always concerned with minimization. We are dealing with maximization, so we are interested in concave functions. That's a big field, but definitely, and this is of course what you can already take from what we discuss here, it pays to look at likelihood functions or log likelihood functions, so to visualize them if you use this concept in a specific model scenario, because it's not necessarily clear that you have a well-behaved, strictly concave function that you're trying to maximize. And it pays to look into that. So if you're more interested in that, maybe have a look at our recent papers on also free energy, which is a kind of generalized likelihood or log likelihood function better, that where we actually visualize things, and then you can see where the maximum is. Yeah, these are more random points that I'm bringing up, which we will not basically pursue much. But what we will pursue is the question of what actually the data is, and that's now the thing with IID data. What seems to be independent data. What seems to be a little bit confusing for people learning about maximum likelihood estimation is that they often do not account for the fact that the y here, this is the data, or better, the data set. Yeah. Because let's first make that explicit with an example. So assume you sample from a univariate Gaussian that has a certain expectation parameter and a certain variance parameter. This describes the case of one value. Yeah. Now, some people then confuse the likelihood function business with the probability density for a single data point. But this is not what the maximum likelihood estimation wants. It wants to it wants to think about the probability of the entire data set. And this, I think, can get clear, or is clear definitely for IID data. So if we now assume that we have individual data points, so scalar individual data points. So we have obtained some data, let's say 2.1, 1.8, 2.7, and 0.5. So this is our data set. For example, we measured reaction times in one participant in 4 trials, and these are the data that we got, or whatever you want to associate with these data. And we want to employ maximum likelihood estimation for some probabilistic model of these data. We have to really think about our likelihood function. And for IID data, for independent and identically distributed data, this is relatively straightforward from what you know already from the way we model stochastic independence in probabilistic models. So the logic is as follows. So you have these data points, and for each one you now invent a random variable, which I'm calling y1, y2, y3, and y4. So these things are random variables. And for IID, you assume that these random variables are all independent. And if you furthermore assume that or postulate a given distribution for each of these random variables, for example, Pi is distributed according to a univariate normal distribution with expectation sigma and variance pi sigma square, where you already see that this mu and this sigma square is independent of the index I. If you postulate this for each individual random variable, and then think about the probability density for all these 4 random variables under the assumption that they are independent, what is the joint distribution? Yeah, so you do a product of the individual probabilities or probability densities in this case, and of course this you can get by in this case by substituting this n y I mu sigma square, and then in this case with the 4 here, and now putting in again the dependence on the parameters. This thing here, this is what this p theta y means. Yeah. So this is really, this really must be your data set, not an individual data point. Yeah, that's important. And for IID data, you can get the likelihood function for a given data set of a specific size by multiplying the probabilities for individual random variables in your probabilistic model. And this has another nice, so IID data has another nice feature. So maybe let's first state that somewhat more general. So for IID data, p theta y corresponds to p theta y1, y2, yn. So if you have n scalar data points, but also if these things, if these yi's are not scalar, same thing applies. So you can use this product for independent data points. So this has another nice feature if you now consider the log likelihood function. So if you apply the natural logarithm, because what do you know? What does the logarithm do to products? Sorry? It turns it into summation over the individual log terms. That's right. So if you have this, you actually get a sum. So maybe note a little bit that so in terms of mathematics, people would not be happy with this notation. So I have p theta of this y, and here I have p theta of yi. These are of course different probability density functions, but you can tell that by looking at the argument. Yeah, so this takes yi and this takes y, and y is the concatenation of these. Let's maybe put that here, the concatenation of these yi. Yeah, and that's also nice then, that's also nice if you have things into a sum, because then calculating with things gets easier. Good, so I think these were the kind of general things that I wanted to say about maximum likelihood estimation. So, so to summarize, if you now summary maximum likelihood estimation, if you're now in the position that you have acquired some behavioral data and you, or even fMRI data or EEG data, and you would like to, and you have some data, and you have like a theory of how this data comes about. If you then have your theory and you have formalized that as a probabilistic model, which in all the papers that you write, as soon as they put in a softmax function, who is in their paper a softmax function, Nobody has a softmax function? Softmax? Reinforcement learning model? No one? What are you doing in these other courses?
We had it a couple of times.
Okay.
Okay.
You don't know what it is?
I don't know.
Yeah, but that's the problem of the other lecturers. As soon as you have as soon as you see that somebody uses the softmax choice rule or something in a reinforcement learning model, what they actually do is they formulate a probabilistic model. So this gets a lot lost in actually this cognitive neuroscience papers, but this is the reason why they then can do maximum likelihood estimation. But they don't. They understand that, of course, but they don't talk about it because they choose not to. So coming back to the scenario that I just described, so you have acquired some behavioral data or some other kind of data, any kind of data, EEG data, fMRI data. Any kind of data, you have formulated your theory of how this data comes about in terms of a probabilistic model, for example, by using a reinforcement learning delta rule and a softmax function. Then you can now go and estimate the parameters using maximum likelihood, but you have to work for that. And the first thing you have to do is that you need to formulate the likelihood function. And even if you say, okay, I don't want to do all this calculus business, and it might not even be possible in this case, if you want to implement maximum likelihood estimation for the model that you're interested in, you have to implement the likelihood or log likelihood function. So you have to program it, and that means you also have to formulate it. So this is what you have to do in any case. What we will also have to do is evaluate evaluate likelihood function derivative. So compute that, which in some numerical routines is then done automatically for you or not done at all. And finally, set derivative to 0. And solve for the maximum likelihood estimate. Yeah, so this is how maximum likelihood estimation works in very general terms, but also as a very general purpose procedure for actually getting point estimates for parameters. Now, of course, yeah, sorry.
So the probabilistic function here, is it probability mass function or probability density function?
Can be anything. So that's a good question. But the way I'm dealing with this notation here all the time is covering essentially both cases. This is why I often say probability distribution, although if you look into measure theoretic foundations of probability theory, that's also the way I use it is not very nice. But it can be both. And because I'm not, this is not the level of rigor that we're striving for, or I'm striving for in this course to get something done, it can be both. And in the examples that we now will see in the GLM and also in the example that we now look at, it's actually a density function. So it's the Gaussian or multiple or product of the Gaussian. But in real life, it's also often a mass function. So depends then really on your model. Good. So other questions right now on this general thing? No. Good. Then I now want to apply this logic of maximum likelihood estimation to a familiar case. Namely, estimating the expectation parameter of a Gaussian from a number of independent samples from this Gaussian for known variance parameter. In the script, you actually find the case where both parameters, the expectation parameter and the variance parameter, are estimated, but because I only have 20 minutes left, I will only do the expectation parameter here, yeah? So this is the very unnatural case that you know the variance of your model, but you don't know the expectation parameter. But it's a good tutorial example. So what do I mean? ML, maximum likelihood estimation of expectation of a Gaussian. So if you think back in terms of how you talked about these things in undergrad statistics and psychology, I assume you learned something about population parameters. Who has the term has heard the term population parameter? So that's also no one. Just a very few people. Then that doesn't really help that I now come back to that. I don't like it that much in terms of populations because real populations are always finite, and what we are dealing with here is actually a mathematical model which is infinite. So for real population statistics in terms of the German population or something, you actually are in the discrete case and things look a little bit different. Anyway, so what do we want to do? Well, what we want to do is the following. We think that, or we conceive the case that we have n data points. So for example, n equals 10. Say n equals 10. And let's say these data points, so these data points can be anything, so it can be 3.1, 4.3, and then we have 10 in this case of it, which then would be 5.1. So this is data that we have observed, and now we want to model this in a probabilistic sense, which means we conceive of y1, y2, and yn as realizations of random variables. So we invent now random variables, which we actually give almost the same names to make the difference clearer. I put a little star here now so that you think these are realizations of random variables. And these are actually the random variables. Yeah? And now we say, okay, we assume that these data points were generated from a univariate Gaussian distribution. And we assume further that all of these n data points were sampled from the same univariate Gaussian distribution with fixed, with true but unknown mu, true but unknown, and sigma square known. Yeah, so we know the value of sigma square. For example, it's 1 or 2 or whatever. And we say that we assume that all of them were sampled from this same distribution with the same true but unknown parameter mu and the same known parameter sigma square, and that the sampling happened IID, so specifically, so the first I we have already seen because they are identically distributed, so that's identical. And the second thing is the independence. Now, if we want to start formulating our likelihood function, we of course have to now conceive our data so as a function of the parameter, which in this case is just the mu, and our data and the way we model it with our n random variables looks like this, for which we now make the independence assumption like previously. So we write it as the product of these n individual densities in this case, or probability distributions, and these individual probability densities we of course have specified here. So we get the product of I n y I mu sigma square, and this of course is equal to 1 2 pi sigma square x minus 1 2 sigma square y I minus mu square. Yeah, hope no mistakes here. So this is actually fairly important. So here we have our p mu y. We have now very explicitly written down the definition of our argument of the likelihood function. Yeah? So this L mu y, where mu is now the thing that was theta before, but in this case our parameter of interest is only the mu, which is defined as this p mu y. We have now written up very explicitly here. Yeah? Everybody happy with that? It's also a question that one doesn't need to ask, but anyway. Good. So that was the first step in our three-step manner. So formulation of the likelihood function. Right? This is actually the most not tricky step, but the most conceptually demanding step, so that you think about what is actually the likelihood function. The rest then is actually uses is just technique essentially. So now one can rewrite this this likelihood function, for example, in terms of a log likelihood function. You could also now go and implement this in a computer and fiddle around with your value of mu, sigma square, you know, and fiddle around until you think you are at a maximum. Yeah. So you can do maximum likelihood estimation as soon as you have the likelihood function. We will now go down the tutorial analytical route to see what kind of formula actually falls out for mu. And to do that, what helps is that we actually consider the log likelihood function. So we do the log transform. So we do how it's defined. So the log p mu y. And this means that we compute the log of this. And actually, we've seen something very similar before. So the log, so the first thing is that, of course, we have all these multiple terms in there. 2p sigma square to the power of n, because this product is n times. And we can, these exponential terms, because we have products of exponentials, we can use the exponential of the sum of these. So we actually have these two sigma square sum e1 to n mu yi minus mu square. This actually we have seen previously. So now if we apply the logarithm, in a couple of steps that you see documented on page 102, we actually get to this form. So how you exactly get there, you see on page 102. So obviously these minus signs come in because here it's 1 over something. The 1/2 comes in because the square root is to the power of 1/2. The 2 pi comes from that. The sigma square comes also from that. And then the log does away with the exponential, so we get rid of the exponential. And this is essentially, so this last part is just the argument of the exponential. So we now have a log likelihood function, and don't go away. And the procedure then says we should compute the derivative of the likelihood or log likelihood function with respect to our parameter of interest. And our parameter of interest is, of course, in this case, mu, because we want to estimate mu. So we can compute d mu L mu y. One could also write this differently so that it would look more like you like it. Oh, actually, I've done something wrong here all the time, right? Why does nobody correct me? You need to pay attention. I cannot do everything on my own. This is a function of mu, and the y should be here. So, like that. So, the important thing is that it's a function of the parameter. And this is specifically important if you now compute the derivative with respect to the parameter. So essentially you can, like we did in the calculus refresher, think about the derivative of the log likelihood function, which in the script you see we have to do partial derivatives because we are looking at 2 parameters, but here we are just dealing with a univariate function, so we can just use the standard derivative. And it's clear that this derivative is with respect to mu. So this is what we are doing now. So let's take the derivative. What's the derivative of this term with respect to mu? Is there a mu in there? No. So then, No, it's no. No. This is like a constant. Ah, that's n. Sorry, that's That's an n. Mu looks like this. N looks like this. So this is like the constant that we've seen in the refresher. So like the 4 that we've seen. So that's 0. The same logic applies here. So this is again a constant. So that's 0. And then here we have this last term. So maybe first we consider, so here what actually helps is to think again of how derivatives work. So then maybe I help you here with that. So the derivative with respect to mu of this thing looks as follows. And then derivatives are linear, so you can put them into products if your variable of interest is there, and then also into sum, because this you can do that without further explaining that. So again, this you all find in my calculus refresher why this is allowed, and essentially you are left to computing the derivative of the thing under the sum. And of course, we've seen that before today. So the derivative of this is, you again need the chain rule. So you have to, so if you do this square, you get, if you do away with the square, you get 2yi minus mu. And now if you do the inner derivative, so you have to form the derivative of minus mu, you actually get -1, so you also get away with the negative sign, so you get actually, this goes away. And then you can also take, because of sums, you can take the 2 out of the sum, and then end up with this. So that is kind of mathematical detail, but what comes out is that the derivative of the log likelihood function for this case is actually given by this. So this is, now we finished the second step of the procedure. So we evaluated the likelihood, in this case the log likelihood function derivative. So this is what we have now. And then the last step in this scenario is that we have to set the derivative to 0 and solve for our maximum point. Yeah, so this is again an analogy to what we've done this morning, so that you this morning, now it's late in the evening, so what we've done in the very beginning, where we computed the derivative of our little function fx there, which was -2 times x minus 3 in brackets, and then we set it to 0 and solved, and to find the value that maximizes it. And exactly the same thing we do here now. So we are writing down, this is actually also called the log likelihood equation. So setting the derivative of the likelihood or log likelihood function to 0 is called log likelihood equation. And so we're setting that to 0. Now we have two things here. One thing is this term, and one thing is this term. Sigma square is always larger than 0, and actually we know sigma square, but also we know that sigma square is always larger than 0. So this term here is always larger than 0, which means that this expression on the left-hand side can only go to 0 if actually the sum term is 0. So we can simplify that further to this scenario. And now we have to think a little bit more about what is actually written there. So it says the sum over n terms yi minus mu. That means there's actually a sum that looks as follows: y1 minus mu plus y2 minus mu plus, going on, plus yn minus mu equals 0. Now, obviously, there's a sum of the yi, so y1 plus y2 plus yn. So we have a sum I to n over yn. And there's a sum also over these minus mu's. So we have minus the sum over mu I from 1 to n. Yeah, so we have to subtract mu n times here. Yeah, and that's 0. So we have, and actually we might carry on this little star to make that explicit. So which again, of course, we can write. So this, I mentioned that somewhere in the beginning, this is the same as n times mu. It's the clash of the titans here. Two things that look weird. So n times mu star and yn n equals 0. And now we can solve for our mu star. So we do minus the sum term. And then we divide by minus n. Oh, we can get rid of the negative sign, of course, the minus sign. And we get the expression for the maximum likelihood estimate of the expectation parameter, which says you should sum up all the data points and divide them by the number of data points. So something that is really familiar to you. So it's, of course, the sample average. It's not surprising. But what is maybe new is that actually this is now not a descriptive statistic, like you can compute an average always, but it's an estimate for a parameter of a probabilistic model, and the probabilistic model is that these are actually normally distributed. Yeah. For the sigma square, you can, in analogy, derive something that looks almost, or that looks like the empirical variance. However, it actually turns out that the maximum likelihood estimate is for the variance parameter is biased, and it's not the unbiased parameter estimate. But this is kind of the analytically, this is kind of the textbook example of the analytical way to obtain maximum likelihood estimates for probabilistic models. Yeah. So I skipped over some details, mathematical details, if you, simple steps essentially. But so you can trace the whole thing in the script. Let me know if you find typos and so on, then I can improve on that. But yeah, kind of this was the example that I wanted to show. Essentially, so to summarize the whole maximum likelihood estimation from an analytical perspective, you have to think back of your calculus of maximizing functions. Then you want to maximize a very specific function, namely the likelihood function, which is a function of the parameter. Once you have formulated it, you can do a little bit of mathematics in simple scenarios, like transforming it to log and computing the derivative and then solving. And then you end up with a rule that allows you to compute parameter estimates. Maybe to find, we'll end in a second. I would call this thing here now an estimator, because you can plug in all different values of yn. If you plug in actually the values that we've seen here, if you plug in these, and of course you need to make up some other values and compute that the estimate is actually, let's say, I don't know, 4.1 or so, that would be an estimate. Yeah? Good, so I'm done. Questions?
If both of the parameters are unknown and how to optimize them.
That's a good point. Yeah. So the way that so if both of them are unknown, one way is that you go one at a time. So you first treat one of them as being known, find the estimate for it, and then based on this, you plug in this estimate as the estimator for the other one. This works actually in this Gaussian case. But however, that means that actually these parameters are independent in some sense. And this is for models that you formulate yourself, not necessarily the case. So there one has to be a little bit more careful. But of course, you can also do simultaneous parameter estimation in the sense that you compute the gradient with respect to the parameters and then use either analytically or numerically a simultaneous maximization with respect to the parameters. So the logic, and it's actually, of course, in applied cases, it's more often than you like, it's the case that you have not only a single parameter, but multiple parameters. So a parameter vector, essentially. But the logic works the same way. Other questions? No. Good. Then.
Could you possibly say again why we put the star?
Why I put the star? Yeah, because we are looking, so the star with the, I mean the same thing as this, because we are solving for this. I just try to make this more explicit. This, but that's the whole thing. It doesn't mean anything. It's just that.
Yeah, I see where it comes from.
So. Okay, so then next time we will actually apply this logic now to the GLM, and yeah, that's it for today, and then see you on YouTube.